Okay, so my name is Ben, and I'm going to be showing you guys this air quality monitor I set up using an Arduino and a flash server to display the data. Okay, so as you guys can see, I have an LCD here reading the temperature and humidity from our DHT11, and we have the MQ135 over here, and that's running our data through Python and then eventually into our flash server here, and it's updating live, as you can see. Okay, so the two components you're going to need for the core of this project is the DHT11 and the MQ135. I'll start by talking about the MQ135. And yeah, I do have an LCD there, but I just had it on my board from before, and I just kind of used it to double check the serial data from the Arduino. So how does the MQ135 work? So at its core, it is a chemoresistor. So there's a resistor in here that is made of tin dioxide, and what happens is the oxygen in the air will inhibit the flow of electricity because it is binding to some of the electrons, and when there's pollutants in the air, they react to those oxygen molecules, therefore reducing the resistivity inside here. And we're reading a voltage out value, but we do have a voltage divider, so when the resistivity goes down, we're reading a voltage out that's going to go up. And I'll show you guys the math here if you care. None of it's too important. The computer does most of it, but... Okay, so on to the DHT11. And the reason why I like the DHT11 and the MQ135 pairing is because the MQ135 does actually vary slightly due to the temperature and humidity, so it's nice to have the DHT11. If you read the MQ135 datasheet, it tells you you should calibrate based on temperature and humidity, and I'll show you guys later on the model I used to predict the changes in the MQ135 resistivity based off the temperature and humidity, but before that, I'd like to talk about the DHT11. Okay, how does the DHT11 work? So inside we have a thermistor and a humidity sensor. The thermistor contains some metal oxides that when a temperature increase occurs, it creates more electron carriers, and we read that as a lower resistance. And I thought the humidity sensing mechanism was actually pretty cool. So we have two electrodes, and in between those two electrodes we have some sort of substrate, which apparently I'm not allowed to know due to proprietary reasons. But that's besides the point. What happens is when the amount of water vapor or when the humidity increases, that creates more ions, or the substrate absorbs the ions from the water vapor, and those two electrodes will read that as an easier flow of electricity. So that's how we read the humidity. Okay, so how did I create a correction model for the resistivity of the MQ135? So I needed to create a formula that interacted with the resistivity based on two variables, that being temperature and humidity. So I just start out with a first order Taylor expansion for two variables, and then I normalize that based off my baseline RS conditions, which I gathered from about like 7 hours of reading. And after that, you have your correction factor, which needs two coefficients for the alpha values, and I pulled those from the MQ135 datasheet, figure 4, which I'll link down below. I took points at 20 degrees and 30 degrees Celsius because I wanted my linear approximation to represent the normal conditions of a house. And yeah, I ended up with this formula here. I'll show you guys. Okay, so there was actually a different approximation that I found from a paper published in 2016 at the University of New Delhi. And the reason I didn't use their correction factor, well, first off, I found this after I created mine, but what they did is they used a much wider temperature range than me, which makes the model much more aggressive, because as you go into the negatives degrees Celsius, there's a ramp up in the difference in resistivity. So it's very unlike conditions you're gonna find in a home. And here's the comparison between my model and their model. It's not too much of a difference, but it is a lot more aggressive, and it's because we both use planar approximations, which I'm not sure why they did that instead of just using like a polynomial function, but yeah. Okay, so into the code base, this is our C++ file right here, and this is what we're gonna pass into the Arduino, and also what we're gonna read from the Arduino. All of this is just instantiation, and this is just telling our C++ file, okay, expect 5 volts and 10 bits from this pin on the Arduino. This is also just setting up our formula. These are our initial values, which we calculate in this calculate average Python folder. It's just reading from the CSV we have up there. I'll show you guys later. This is all set up. This is telling the MQ135 or telling the C++ file to read on a logarithmic scale, because that's how the MQ35 recognizes the gas particles in the air. And then here we have our correction formula. It says get the RS value and then apply our correction formula to that, and that's your new RS value. And yeah, and then we just print it out to the serial, which I'll show you guys here. Okay, now you can see we're reading data from the Arduino and it's passing in here. And then next we go to our Python file. Okay, so now we're in our Python file, and all this is just importing libraries that we need. And here's where it gets interesting. So we create our arrays for humidity, temp date, and timestamps. And then right here, we say, okay, read it from here, read it from your Arduino terminal. And if you see humidity, temperature, and RS, split them up and put them in their respective arrays. And then if you don't have a CSV file yet, create that and write your data frame into the logs corrected CSV. So as you can see here, it's not reading live, but I can get it too. If I just run my Python file, let's wait for it. Okay, it's running in Python, reading from the Arduino, and if we go into logs corrected, yep, there you go. Okay, so now we're in our app.py file, which is where our Flask server is located. So we import pandas and Flask. Pandas is just like to organize data, and Flask is what we need to create our local server. So our first function is the read CSV function. So first we connect a path to the CSV, and then we read the CSV, right? If there's temperature, if there's humidity, etc., etc. Down here, we have our functions for the JavaScript file and HTML file. So if someone loads up the website, read from the HTML and create the front end. And right here, we have a function that pretty much just transforms the data into a JSON that the JavaScript can read, right? So we call a read CSV function and say, okay, find the data, if there is data, and then return it as a JSON. And we can see here that the JavaScript, every time it tries to refresh the data, it is calling fetch API latest, which was the function we just created in our app.py. And I'll go right into here. So all the JSON really serves to do is to pass data to the HTML and create some plots for us. So here we're telling the HTML, this is what you're seeing. If you look in here, we can find those same element ID values, and that's just saying, okay, this is where we're going to put this on our web page, right? And let's go back into the JSON. So if we scroll down, we have the charts that the JSON is creating. So here are your charts. This is the data you're going to pass in, and this is the layout, right? And we just use Plotly. We have, as I talked about earlier, the refresh data function, which is just calling our app.py. And right here, this is the important part, the event listener, and it's as .com is loaded, we constantly refresh the charts and call the refresh data function. So we're constantly getting new data from the app.py. And the last thing I'll do is show you guys my HTML file. So all of this in here is just saying, okay, this is how I want the website to look. Down here is the important part, which is, okay, take the IDs from the JSON, and pass them into our specific locations. And this is the JSON you're going to be reading from, static main JSON, which we have in here. And yeah, that's all of my code base. So I'll go right into showing you guys the website. Okay, so here's the finished product. Temperature, humidity, air quality, live updating. Right now the graphs have 66,000 data points, which is a little bit excessive, but yeah. Okay, and I just want to say thank you to anyone who made it this far in the video. I'll be posting again soon, so see you then.